A missile traveling close to 4 miles every second is detected moving toward its target. At that velocity, a weapon can cross the width of a metropolitan area before most people could read a short paragraph. When speeds approach Mach 15, roughly 11,000 miles per hour, defenders may have less than a minute between initial detection and impact. That is the situation confronting military planners after Iran demonstrated the Fattah hypersonic missile against Israel. The immediate concern is simple. If this type of weapon cannot be intercepted, large sections of regional defense architecture become ineffective. The central question now facing governments and military alliances is whether existing systems can adapt quickly enough to counter a new generation of maneuverable hypersonic weapons. Traditional missile defense relies on prediction. When a ballistic missile launches, it follows a path shaped largely by gravity and initial propulsion. Radar systems track that trajectory. Computers calculate the likely impact point, and interceptor missiles are launched toward the predicted location. Systems such as the Patriot missile system and Israel's Arrow missile defense system are built around this concept. Their success depends on solving a complex geometry problem quickly and accurately. Hypersonic glide weapons undermine that entire model. The Fattah hypersonic missile combines extreme speed with the ability to maneuver while in flight. Instead of following a stable ballistic arc, the vehicle can shift direction during the later stages of its trajectory. At Mach 15, the missile travels roughly 3 to 4 miles every second. During the time required for radar systems to confirm the threat, generate an intercept calculation, and launch a defensive missile, the target may already be dozens of miles closer to its destination. Speed alone presents difficulties, but maneuverability introduces a deeper challenge. Interceptor systems are programmed to strike a predicted point in space where the target will arrive. If the incoming weapon changes course even slightly, the intercept calculation becomes inaccurate. At hypersonic velocity, a small deviation can translate into several miles of difference by the time the interceptor reaches the predicted location. The margin for defensive error becomes extremely small. Another complication comes from physics itself. Objects moving through the atmosphere at extreme speeds generate intense heat through friction. That heat produces a layer of ionized gas known as plasma around the missile body. This plasma sheath can interfere with radar signals, sometimes scattering them or weakening their return signal. As a result, tracking data can appear unstable, forcing defense systems to operate with incomplete information. Iran's hypersonic program is the result of years of incremental development. Iranian engineers have long invested in missile technology as a strategic equalizer against more technologically advanced militaries. According to open-source assessments, the program drew on a mixture of domestic research and external technical knowledge, including publicly available studies on high-speed aerodynamics and guidance systems capable of functioning under extreme thermal conditions. The system appears to follow a two-phase flight profile. A solid fuel booster initially accelerates the weapon to hypersonic speed shortly after launch. Once sufficient velocity is achieved, the payload separates and continues as a glide vehicle, using aerodynamic lift to travel through the upper atmosphere. This glide phase allows the vehicle to maintain very high speed while remaining lower than traditional ballistic missiles that arc into space. That lower altitude can shorten detection times for early warning sensors. During the final approach, the vehicle descends toward its target while retaining the ability to adjust course. These terminal maneuvers complicate the calculations required for interception. For defenders, the result is a compressed timeline. Detection, identification, interception planning, and missile launch must all occur within a window that may last less than 1 minute. Iran's decision to use such a weapon carries strategic signaling beyond the immediate military impact. Demonstrating hypersonic capability in combat conditions communicates a message not only to Israel, but also to regional powers and outside actors with military forces in the Middle East. The message is intended to show that Iran possesses weapons capable of bypassing existing missile defense systems. Israel's layered defensive network was designed primarily to counter rockets and ballistic missiles. The Iron Dome focuses on intercepting short-range projectiles. David's Sling targets longer-range threats. Higher altitude interception is handled by the Arrow system. These layers together create protection against a wide spectrum of conventional missile threats. Hypersonic glide vehicles, however, were not part of the original design assumptions. For the United States, the implications extend to its military presence across the region. Bases in countries such as Kuwait, Qatar, and the United Arab Emirates host airfields, command centers, and logistics hubs that support American operations. Many of these installations rely on defensive systems similar to those protecting Israel. If hypersonic weapons can penetrate those defenses, the vulnerability of forward-deployed forces increases. Naval operations face similar questions. Modern warships depend on layered defensive systems such as the Aegis combat system to intercept incoming threats. These systems are highly capable against conventional missiles. Against maneuvering hypersonic weapons, however, reaction time becomes a major limitation. A ship may detect the threat but still struggle to generate an intercept solution quickly enough. The broader concern is technological diffusion. Once one country demonstrates a capability in combat, other nations begin evaluating how to obtain similar technology. Countries including Turkey, Saudi Arabia, and Egypt may reassess their own missile programs in response to this development. At the global level, major powers are already pursuing hypersonic systems. Russia has introduced weapons such as the Kinjal missile and the Zircon missile. Meanwhile, China has tested the DFZF, reflecting a broader race among major powers to develop high-speed maneuvering weapons. Defensive solutions are still under development. Concepts include directed energy systems, high-power lasers capable of damaging incoming weapons at long range, and electromagnetic railguns that could fire interceptors at extreme velocities. Artificial intelligence-assisted tracking systems are also being explored to predict the movements of maneuvering targets faster than human operators can respond. None of these technologies are yet widely deployed. As a result, the balance between offensive and defensive missile technology may be shifting. Hypersonic weapons currently exploit gaps in the defensive architecture built over the past several decades. Detection systems themselves may also require redesign. Radar networks that track ballistic missiles depend on consistent signal reflection from the target. Hypersonic flight conditions can distort that signal. Space-based infrared sensors can detect heat signatures, but the warning time provided may still be too short to allow reliable interception. The consequences extend beyond the battlefield. Military planners must reconsider the survivability of high-value assets such as airbases, naval fleets, and critical infrastructure. If weapons capable of traveling thousands of miles in minutes cannot be intercepted reliably, defense strategies will increasingly rely on dispersal, redundancy, and deterrence rather than interception alone. Arms control frameworks also face new complications. Hypersonic delivery systems can carry conventional or nuclear payloads, making it difficult to determine the nature of an incoming strike. Their speed also compresses decision-making time for national leaders, increasing the risk of miscalculation during crises. Iran's demonstration of hypersonic capability therefore represents more than a single technological milestone. It signals a broader shift in the strategic environment where smaller states can field weapons that challenge traditional military advantages. The immediate effect is uncertainty. Military alliances, defense planners, and governments must reassess assumptions that guided defense investments for decades. Whether defensive technology eventually restores balance remains an open question. For now, the emergence of maneuverable hypersonic weapons marks a new phase in the evolving contest between missile offense and missile defense.